Experiment M11. Rotational dynamics. Objective: to find the moment of inertia of the inertia wheel set. Equipment: 1. Inertia wheel set. It consists of a wheel and an axle. The wheel has mass md and radius rd, and the axle has mass mh and radius rh. The mass and radius are specified on a sign posted on the test table. 2. Weighted saucer with rope. The mass of the saucer, M0, has been written on the saucer. 3. Weight set. It consists of one mass of 100 grams, one mass of 50 grams, two masses of 20 grams each, and one mass of 10 grams. The weight set is provided in the equipment box. It is complete and can be used for testing. Students are prohibited from borrowing weight sets from other student groups. 4. Tape measure. 5. Stopwatch. Theory: when a mass m moves downward with linear acceleration a, the tension T in the rope causes a torque to act on the inertia wheel set. This torque results in the wheel rotating with angular acceleration alpha. The relationship between torque and alpha satisfies Newton's second law of motion for rotational motion. Newton's second law of rotational motion. Torque equals I alpha. Torque tau is caused by the rope tension acting on the inertia wheel set at the edge of the shaft, where I denotes the moment of inertia of the inertia wheel assembly about the axis of rotation passing through the center of mass. The axis of rotation is perpendicular to the plane of the wheel. Alpha is the angular acceleration of the inertia wheel set. The moment of inertia I can be theoretically calculated by using the given mass and radius of the wheel and axle system. I equals 1/2 mdrd squared plus 1/2 mhrh squared. Where md is the mass of the wheel, rd is the radius of the wheel, mh is the mass of the axle, and rh is the radius of the axle. The torque acting on the inertia wheel assembly due to the tension force T acting on the system at the edge of the black shaft is torque equals RH cross T. RH is a vector pointing from the axis of rotation to the position where the rope tension T acts on the system. The figure shows that vector RH and vector T are perpendicular to each other, making an angle of 90 degrees. Torque is a vector quantity possessing both magnitude and direction. The direction of torque is determined using the right-hand rule. From the picture, it is observed that the torque is inward, and its magnitude is given by torque equals RH times T, where RH and T are the magnitudes of vectors RH and T, respectively. If you know the magnitude of the rope tension T, you will immediately know the torque acting on the system. We can determine the tension force of the rope from the linear motion of mass m. Considering the linear motion of mass m, where m equals the mass of the saucer m0 plus the added counterweight. When a mass is allowed to move from a height h with an initial velocity u equals 0, two forces act on the mass, the weight mg acting downward and the string tension T acting upward. Therefore, according to Newton's second law of motion, the net force acting on the mass m has a value equal to mg minus T equals ma. We formulate the equation to find the tension in the rope. The tension force in the rope is equal to T equals m multiplied by g minus a. When g equals 9.782 meters per second squared, we find the linear acceleration a from the mass release experiment by measuring the time it takes to move. Substituting T into the equation torque equals TRH, we can express torque in terms of linear acceleration a, mass m, and shaft radius RH. Torque equals m multiplied by g minus a multiplied by RH. We will use the linear acceleration obtained experimentally to calculate the system's torque when releasing mass m. After obtaining the torque, we determine the angular acceleration alpha. Alpha equals a divided by RH. In rotational motion, we have Newton's second law expressed as torque equals I alpha. A graph showing the relationship between torque, tau, and angular acceleration, alpha, can be used to determine the system's moment of inertia, I, where the slope of the graph, g, equals the moment of inertia. In the experiment, students will release masses of varying sizes, m, and measure the time it takes for them to descend from a height h. They will use this time to calculate the linear acceleration a. Then, they will substitute the linear acceleration into the equation. Torque equals m multiplied by g minus a multiplied by rh. And substitute the value into the equation. Alpha equals a divided by rh. Linear acceleration a can be obtained from the following experiment. The mass moves downward with a constant linear acceleration a and initial velocity u equals 0. It takes time t to achieve displacement h. Substitute the values into the equations of motion with constant acceleration. H equals ut plus 1/2 at squared. Since the initial velocity u equals 0, linear acceleration a is given by a equals 2h divided by t squared.